Hi everyone, in this video we're going to talk about related rates. So you should be watching this after you've read through the first example in the related rates notes. So let's start by talking through roughly what we did in this example and what we can expect to be common in the future examples. So this is the same paragraph that you have in your notes where they're describing oil leaking onto water, so it forms a 1/2 inch deep circular puddle, which I've drawn here. And we're asked to find the rate of change of the radius at the moment that it's 5 inches. So notice they have to give that piece of information because as we're adding volume to the puddle, the radius is getting larger and larger as the puddle grows. So they have to tell us, what is the rate at a particular moment, because the rate will be changing as well as the radius. All right, so I have a few bullet points to start of me kind of collecting information, labeling things as math. So I'm noticing that the radius would be increasing. We're looking for dr dt because they want the rate of change of the radius at the moment that r is 5. And they're telling us that dv dt is 3. I can tell that because of this line right here. The oil is leaking at a rate of 3 cubic inches per second. So that's telling us an increase in volume. So the volume is increasing at a rate of 3. Okay, so I said, well, I know that the volume of this cylinder, this is the really short version of a cylinder, but still a cylinder. So its volume equation is pi r squared h. I know that h is always a 1/2, that's the height of the puddle. From that very first, from that very first piece of information there. So I plugged in a 1/2 for h, and then I took the derivative of each side with respect to t. So this is where implicit differentiation comes into play, right here. So what I've done is treat the v and the r sort of like we were treating y in the implicit section. So v's derivative is just 1, but then it was supposed to be with respect to t, so I'll give it a dv dt. Same thing over here, pi over 2 carries down, r squared goes to 2r to the 1 power, but then r wasn't t, so we get dr dt here. So we've taken a derivative with respect to a variable that isn't actually in the equation. That's what's going to happen in pretty much every related rates example. So you'll have more than one derivative once you actually take derivatives. You'll have more than one rate change, hence related rates. All right, so in this line I said, oh, well, I have values for a lot of these things. I know dv dt is 3. I know at this particular moment r is 5, and this is what I'm solving for. So once I plug stuff in, I just algebraically solve for that number. And then of course our final answer is down here. It's about 0.191. I threw in inches per second. You won't be responsible for, you won't lose points if you don't put units on things in this class, because I'm more concerned with you doing the math. But if you are in some sort of engineering or physics major, I encourage you to try to track the units as you go and put them in at the end. Okay, so what the heck is going on? All right, so now we're going to move on from the notes here and talk about some things to expect. So the first thing is generally what'll these problems look like, right? They'll all be word problems, they'll all be different. But in general, you'll be given some sort of scenario, like the puddle. It'll be different every time. They'll tell you some values of things, a radius is this, a volume is that. And they'll tell you the value of somebody's derivative. It'll look different every time, but they'll give you the rate of change of something. And then here's the key. In each of these word problems, you're going to be asked to find the derivative of something else, right? So you'll be given some kind of derivative, let's say dA dt, the rate of change of some kind of a, and then you'll be asked to find a different derivative, let's say dB dt. That's the rates part of related rates. So your task will always be to find a derivative. Now, what we did in this puddle example was we got the volume and the radius together in an equation and started taking derivatives. That is going to be your goal in all of these. So to put together the equation, you want to identify what these derivatives are. So if I have dA dt and I want dB dt, that means I would need A and B, you know, whatever they stand for in that particular scenario, need A and B in an equation. Don't worry about their derivatives, right? Because you're going to take the derivative of that equation. So it's not like you need the derivatives to kind of be there in the first place. They'll show up. Just worry about getting the variables themselves together, then take the derivative, d dt, that equation on both sides, then plug stuff in, and then algebraically solve for the derivative that you need. So in this plug-in step, you should have enough information to plug in for everything except for the derivative that you need. Every once in a while, you'll run into a problem where, you know, there's one particular value that you don't have to plug in, but you should be able to backtrack and kind of have enough information to figure out what it would be. So don't freak out. Once in a while, there's like one thing to go back for in this step, and that's okay. All right, so one more discussion before we continue here. This is always a big question related to rates. When do I plug stuff in? And by that I mean, we'll come back to our puddle example here in the notes. See how in this example, I plugged in h equals a half right away. I said, okay, well the puddle's, you know, a ½ inch deep. Then I took derivatives and then I plugged in the r, right? Why did I plug in the h up here but the r down here? That's something that you always are going to want to give an extra thought to as you do these problems. And the answer is that the puddle was always a ½ inch deep. Always, always, always. So as the radius changes, at least, you know, in this hypothetical scenario, the problem is implying that that is always the height. That means I'm free to plug it in up front. And really, the more you can plug in first, the better, because that makes your derivative step much easier, right? If we had two variables here, we'd end up with the product rule, it'd be a whole thing. But without it, it was much smoother. I couldn't plug in a value for r right away, because the radius of the puddle was changing. When they say r equals 5, that's kind of like a snapshot moment, right? Find dr dt at this moment. That's telling you that you should not plug that in before the derivative step, right? So the dividing line is the derivative step. Once you take derivatives, you can plug in whatever you want and you're good to go. So you want to be a little extra cautious. If you're not sure if it's always that value, don't plug it in, right? It should be able to take care of itself later on anyways. So plug in before the derivative step if it's always that number. Plug in after the derivative step if it's a snapshot moment data. So the distinction here is before differentiating and after, and this would only be if it is a constant value. And then after differentiating is everything else. Everything is okay here.